Okay, so as we left off, we're going to be moving on to quadric surfaces. Before we do, though, just a quick comment about the calculator, though. When we're looking at this feature of our graph, I did want to say that you could use your right or left arrows to rotate this shape. Didn't mention that in the last video. You can go up or down and gain some different perspectives. What you're going to notice, though, is that sadly, you don't have axes drawn in. One other thing, if you do have to zoom in, I suggest that you also then zoom out. Otherwise, you can get some very bizarre pictures as you move on to your next graph. So remember, hit zoom out. You'll have to hit enter twice, and then it will more or less reconfigure your screen to that original format. But again, now it's going to look more like a line rather than that traditional cylinder. Well, that being said, we're now moving away from cylinders. We're getting into surfaces. There are quite a few of them. We are going to try to make rough sketches graphing them. And let me encourage you with this much. We're doing this because we're going to apply calculus to many of these figures. We're going to find out what it means to take derivatives and integrals and limits and all that good stuff. We've really yet to get into the calculus, and it is a calculus class. But this is really the rationale as for why we're even going through this. You won't really have to graph figures like this in the future. Frankly, machines can graph them better, but we do at least have to demonstrate that we can understand what we're dealing with in a general sense. You will be given a little guide to help you graph these, even on the test. I'm going to be emailing out that guide to those of you who are absent, and you can more or less see what we have right here. A reference to an ellipsoid. This is why I opened the last video with reviewing conics. You could have a three-dimensional ellipse. And let's see what that might look like. Now again, because z is being squared here, you can see, and by the way, if you ignored z just for the briefest of moments, that would look exactly like an ellipse itself, giving reason that this might be a three-dimensional ellipse. But because z is being squared, it's unfortunate that the TI-89 really wouldn't be quite as helpful. That doesn't mean it's not going to be helpful at all. It's just that we'd have to enter in two equations for z, solving for both square roots, and it's kind of cumbersome. But look, cutting to the chase, you could say, well, I would guess that I would have 1 squared down below. I'm going to move 1 step in the x direction from my center. Clearly I'm at 0, 0, 0. Down below I'd have 3 squared, so I'd say 1, 2, 3 steps here in the y direction. Similarly, 3 steps in the negative y direction. For z, you can see, well, this looks like it's 2 squared, so maybe going up 2 and down 2. And my scale is anything but perfect. Let's make sure we get that. But look, what you can do is begin to make some rough pictures. You can say, I would think that going from here to here, also down here, we can make this dotted. You could say going from the y's, we can come way up on top, come down here, down below, and you could draw a few more little ovals here. Again, giving a rough idea, and you can even draw another one if you'd like, that this is looking like a three-dimensional ellipse. Again, when it comes to the test, we're actually not even going to have a problem where you have to technically make a graph. We'll be identifying graphs through matching and also identifying with a lesson that we'll see for next time, but that's just to get you started. Okay, elliptic paraboloids. If you're going to take a look at an elliptic paraboloid, you probably see this word paraboloid. You probably think of a parabola. Indeed, that is what we're going to be looking at. Now, just to say this much, here a TI-89 might be a little bit more easy to use, but again, just to be very frank with you, it's rather hit or miss sometimes whether you're going to get a great picture. So here's what's going on. We could make a real quick sketch. You might think we're going to get a three-dimensional parabola when you see this, and indeed we are. Imagine you're going back to Calc AB and Calc BC, where we revolved a parabola around its axis, and we got a general shape, something like that. This is what we'd expect to see here as well. And certainly as we're trying to get a couple ideas, just to let you know, for example, we could talk about traces. We could say, what about the XZ trace? If we talk about an XZ trace, this means that Y would equal 0. If I'm using two letters in a trace, the missing letter is implied to be 0. This would be the equation Z equals 4x squared. And what we're really getting at is on a ZX plane, on a two-dimensional kind of a graph, we would expect to get a skinny parabola. It would look something like that on the ZX plane. You could say, well, where is the ZX plane? Well, imagine we erase the Y-axis. You could say, well, my goodness, I would kind of envision a kind of skinny parabola, kind of like that. You could say, well, what about the other trace? What if we just looked instead at, we had the XZ trace, how about a YZ trace? Of course, that means x equals 0. If x is equal to 0, you'd have z equals y squared. Very, very similarly, you could say, well, that would be a z-axis, and down here would be my y-axis. You'd say, well, that would look like a parabola. You bet. What would that look like? Well, we'd have erase the x-axis, if you would, and we could say, well, this won't be quite as skinny. Maybe it's looking more like that. Now, just from right here, you might guess that we're going to have a really good idea as to how this is looking. Indeed, we would. You can say, well, I certainly think it would look something more like that. At least getting a rough idea. I do want to make one more comment. Something that you could do is you could let z equal 1. If z is equal to 1, you get 1 is equal to 4x squared plus y squared. This would be 1 equals x squared all over 1/4 plus y squared all over 1. This is an ellipse. This is an ellipse. Your x direction would be 1/2. You'd say just before, like if you had x squared over a squared plus y squared over b squared equals 1. Well, of course, that is going to entail the square root of the number down below. So you could see that we'd go 1/2 in the x direction and 1 full step. We'd get an ellipse when z would equal 1 right up in here. So, of course, that's more or less what we're seeing. Circular paraboloids. Well, my goodness, what if these numbers down below were the same? Well, you'd probably immediately think, well, my goodness, I would guess that it's the same general shape, but instead of up on top having an ellipse for z equals 1, you'd have a circle. You know what? That's exactly it. That's exactly it. So, it's virtually the same appearance, of course. You can say, well, I think we'd get a circle here, and, and so on. The elliptical cone, I don't have a specific numeric example here. However, when you have z squared, so very often kids will note that this equation right here, x squared over a squared plus y squared over b squared on the left, they'll say, wow, this is exactly the same thing as what we just saw up here. Well, no, actually, for the paraboloid, z wasn't being squared. Z was to the first power. What if z was raised to the second power? Well, we could go through an incredible amount of detail and talk about what's happening here. We could even plot some points, but suffice it to say we would get an elliptical cone. What would that look like? Well, it'd be just like a traditional cone that you'd see in geometry. Down below here you'd get another cone. So this is the double-naped cone that you'd see in the pre-calculus course. If you were to let z equal different values, the right-hand side, possibly could be 1 if z equals c. It could be other values, but when you divide both sides so that this right side is a 1, you'd always have ellipses. So you'd get all of these ellipses stacked on top of each other for different z values. And obviously as z is growing larger in absolute value, like if z goes from 1 to 2, or from -1 to -2, -2 is bigger than -1 in absolute value, this right side becomes bigger, so then you divide by it, and these denominators over here get larger too. Alright, let's real quickly take a look at the hyperboloid of one sheet. The hyperboloid of one sheet, you can see right now the right-hand side, must equal 1. We have x squared plus y squared, each over an a squared and a b squared respectively, but the z is being the term that is subtracted. One thing I want you to notice is that there is one minus sign. There's just one minus sign. What we could very quickly point out, and we could do this a couple of different ways. We could graph this via traces. We could graph this for different particular z values. But what you're going to see is really a shape where, up on top, you get something more elliptical, down here, and we're going to continue something just like this. Maybe you've seen shapes like this. Sometimes there's some coffee cups that kind of have this general shape. Some nuclear reactors in their towers have these shapes. In fact, our textbook has a picture of this as well. But of course, what we're really getting at is for different z values, you could show that you get some ellipses as these intersections, but we get some narrowing out here in the middle. But again, with one minus sign, this is going to be one sheet. One other thing I think is so important to talk about, this is in fact incredibly important. For this problem, when z is negative, we're going to have this figure really having its central axis being the z-axis. If we would have had our y term being negative, and this is just a quick comment, and this is so true for these other shapes as well, and I think we need to talk about that. You'd say, hey, what if the y would have been negative? Well, it's still a hyperboloid. It definitely is, except now it's about that y-axis. It's looking more like that. And if x was negative, it would have had a central axis about the x-axis. Likewise, when we come back here to the cone and so forth, if z on the right side, if we would have had an x squared and had z squared on the other side, our cone would have had an axis about the x-axis. Right here, this determines the axis, and that's actually very important to mention, even with the paraboloid, of course. All right, well, we're running a little short on time. With two minus signs, you can see really quickly we're actually going to get a hyperboloid of two sheets. You can think, well, what on earth would that look like? Well, it's going to look something like this. Okay, we're going to wrap up with the last example. It's a little bit more detail in a few minutes, but that will wrap it up for the lesson.